Chapter 3, Atoms and Molecules. Historical background. In the 6th century BC, an Indian philosopher Ganad suggested that matter is composed of very small, indivisible particles. That is, Parmanu, which means the smallest particle. Later, in 430 BC, a Greek philosopher, Democritus, postulated that matter is made up of very small particles which were termed as atoms. In 1808 AD, an English chemist, John Dalton, gave a systematic idea about the structure of an atom. His ideas are grouped together and known as Dalton's atomic theory. By the end of the 18th century, scientists proved experimentally that matter exists in the atomic state and the molecular state. Scientists were interested in knowing how matter combined with each other, why they combined with each other, and how they combined. Scientists formulated the laws of chemical combination after performing many experiments involving chemical reaction. Let's do a quick check. Laws of chemical combination. Law of conservation of mass. Activity. Let us perform a small activity. Take a solution of calcium chloride in a flask labelled A and a solution of sodium sulfate in a test tube labelled B. Tie a thread to the test tube and carefully lower it in the flask. Cork the flask to make it airtight. Now weigh the flask on a balance. It weighs 300.23 grams. Now tilt the flask and allow the contents of the test tube to come in contact with the contents of the flask. Do you observe any change in the flask? Yes. Calcium chloride reacts with sodium sulfate to form a white precipitate of calcium sulfate and a solution of sodium chloride. Now weigh the flask again. Is there any change in the weight of the flask? No, there is no change in the weight of the flask. It again weighs 300.23 grams. What can we say about the mass of the products and the reactants? The mass of the products is equal to the mass of the reactants. Scientists noticed that if chemical reactions were carried out in a closed container, there is no change in the mass. The total mass of the products is equal to the total mass of the reactants. This led to the formulation of the law of conservation of mass. Antoine Lavoisier stated the law of conservation of mass as matter is neither created nor destroyed in a chemical reaction. Law of constant proportions. Proust analyzed the chemical composition of a large number of compounds to determine the type of elements present and the percentage of the elements present in them. He came to the conclusion that each compound had the same elements in the same proportion irrespective of the source from which it was obtained or the method used for preparation. Based on these observations, he formulated the law of constant proportions. According to the law, in a chemical substance, elements are always present in a definite proportion by mass. For example, water obtained from any source will have the same two elements, hydrogen and oxygen, present. The proportion of hydrogen and oxygen is 1:8 by mass. This proportion will always remain the same irrespective of the source of water. Similarly, carbon dioxide obtained from any source will contain the same two elements, carbon and oxygen. Carbon dioxide obtained from any source will always have the proportion of carbon and oxygen as 3:8 by mass. Let us study some more examples. Copper carbonate prepared in the laboratory or isolated from nature will always contain the same elements, copper, oxygen and carbon. The proportion of copper, oxygen and carbon will always remain 5:4:1 by mass, irrespective of the source of copper carbonate. Dalton's atomic theory. His theory is the basic theory about the nature of matter. According to his theory, all matter, whether solid, liquid or gas or element, compound or mixture, is composed of small particles called atoms. The postulates of Dalton's atomic theory are: matter is made up of atoms. Atoms are the smallest indivisible particles of matter. Atoms of a particular element are all alike, but they differ from atoms of another element. Atoms of each element have a characteristic mass. Atoms are indestructible, that is, they can neither be created nor destroyed. Atoms combine to form molecules. A molecule is the smallest unit of a compound. Dalton's atomic theory was based on the laws of chemical combination. The postulate of Dalton's theory that atoms can neither be created nor destroyed was the result of the law of conservation of mass given by Lavoisier. Since an atom cannot be created nor destroyed, therefore the number of atoms in the products of a chemical reaction is the same as the number of atoms in the reactants. The mass remains the same in a chemical reaction. This is the law of conservation of mass. The postulate that atoms of each element have a characteristic mass was based on the law of constant proportions. The number of atoms, the kind of atoms, and the mass of atoms of each element in a compound is fixed. Therefore, in a compound, the same elements combine together in the same proportion by mass. This is the law of constant proportions. Let's do a quick check. Concept of an atom. Have you ever noticed a mason building walls? When four walls are joined together, a room is formed. A collection of such rooms forms a building, small or big, like a house or a skyrise. Now, when you look up towards these buildings, can you tell? What are the building blocks of this building? Of course, the bricks. Let us consider another example. When we break a large crystal of salt, we get tiny grains. Well, it is hard to see just one little grain of salt. The tiny grains are the building blocks of the large crystal of salt. The building blocks of all matter, of which different substances are made, are called atoms. We know that an atom is very small in size and that an atom consists of the subatomic particles protons, neutrons and electrons. Atoms are so small that they cannot be seen even under the most powerful microscope. About 1 million atoms stacked up one over the other would roughly equal the thickness of a sheet of paper. The size of the atom is indicated by its radius, which is called the atomic radius. The atomic radius is measured in nanometers. 1 nanometer is 1 divided by 10 raised to 9 meters or is 10 raised to minus 9 meters. Chemical symbols of elements. Dalton was the first scientist to use symbols for elements. He used circles to represent elements. Berzelius suggested that the symbols of elements be made from 1 to 2 letters of the name of the element. Now, we use names and symbols decided by IUPAC, that is, the International Union of Pure and Applied Chemistry. The names and symbols decided by them are used all over the world for international trade. Many symbols are the first letter of the name or the first 2 letters of the name of the element. The first letter of a symbol is always written as a capital letter and the second letter as a small letter or letter in the lower case. For example, the symbol for the element hydrogen is H. Cobalt is CO. Calcium is Ca. Symbols of some elements are formed from the first letter of the name and a letter appearing later in the name. For example, the symbol of cadmium is Cd. Magnesium is Mg. Some elements have Latin, German or Greek names. Their symbols are derived accordingly. For example, the Latin name for sodium is natrium and its symbol is Na. Iron is ferrum. Its symbol is Fe. Atomic mass. How did scientists weigh atoms? Hydrogen was taken as a standard for measuring atomic masses. Scientists compared the mass of an atom with the mass of hydrogen to determine their relative atomic masses. Hydrogen being the smallest atom, its mass was taken to be as 1 unit. For example, if 1 atom of nitrogen weighs as much as 14 atoms of hydrogen, then the atomic mass of nitrogen is 14 units. Similarly, if 1 atom of sodium weighs as much as 23 atoms of hydrogen, then the atomic mass of sodium is 23 units. Later, carbon-12 isotope was chosen as a standard for measuring the atomic masses. Carbon-12 atom is that atom of carbon which has 6 protons and 6 neutrons in its nucleus. A carbon-12 atom has been assigned an atomic mass of 12 units. The atomic mass of an element indicates the number of times 1 atom of the element is heavier than 1/12 of a carbon-12 atom. For example, 1 atom of sodium is 23 times heavier than 1/12 of a carbon-12 atom. Thus, the atomic mass of sodium is 23 units, which is the average relative mass of the atom of sodium. One atom of hydrogen is as heavy as 1/12 of a carbon-12 atom. Thus, the atomic mass of hydrogen is 1 unit, which is its average relative mass. Let us discuss the average relative atomic masses of some elements. Hydrogen is 1 unit. Carbon is 12 units. Oxygen is 16 units. Sodium is 23 units. Magnesium is 24 units. Calcium is 40 units. Sulfur is 32 units. And chlorine is 35.5 units. How do atoms exist? Atoms of few elements like noble gases like helium, neon, argon and krypton, etc. exist in the free state, that is, as single atoms. But most of the elements being chemically reactive do not exist in the free state. They either exist as molecules or as ions. For example, an iodine crystal is a collection of many iodine molecules. These molecules are so tiny that they are not visible by the naked eye. But what is visible is the entire iodine crystal. Similarly, in sodium chloride, the sodium ions and chloride ions, being so tiny, are not visible. But we can see the compound sodium chloride as a white powder, which is made up of several sodium and chloride ions. Let's do a quick check. Molecules. As the basic unit of an element is an atom, similarly, the basic unit of a compound is a molecule. An atom is not found in the free state, but a molecule is found in the free state. A molecule is made up of two or more identical or different atoms of elements. For example, a molecule of oxygen is made up of two atoms of oxygen. Similarly, nitrogen molecule is made up of two atoms of nitrogen. But a molecule of water is made up of two hydrogen atoms and one oxygen atom. Molecules of elements. The number of atoms present in one molecule of an element is called its atomicity. The molecules can either be monoatomic or diatomic or triatomic or tetraatomic or polyatomic, depending on the number of atoms present in them. Monoatomic molecules. A molecule is said to be monoatomic when it contains only one atom. For example, the noble gases like helium, He, neon, Ne, argon, Ar, krypton, Kr have one atom each in their molecule. So, the atomicity of noble gases is 1, and hence they are monoatomic. Some metallic elements like sodium, Na, potassium, K, magnesium,
Mg, calcium, Ca are also considered to be monoatomic. Diatomic molecules. A molecule is said to be diatomic when it contains two atoms. For example, elementary gases like hydrogen, H2, oxygen, O2, nitrogen, N2, chlorine, Cl2, all have two atoms each in their molecule. So, their atomicity is 2. Hence, they are considered to be diatomic. Triatomic molecules. A molecule is said to be triatomic when it contains 3 atoms. For example, ozone, O3, has 3 atoms in its molecule, and so the atomicity of ozone is 3 and it is said to be triatomic. Tetraatomic molecules. Phosphorus, P4, has 4 atoms in its molecule, and so the atomicity of phosphorus is 4 and it is said to be tetraatomic. Polyatomic molecules. A molecule is said to be polyatomic when it contains more than 4 atoms. For example, solid sulfur, S8, has 8 atoms in its molecule, and so the atomicity of sulfur is 8 and it is said to be polyatomic.
Molecules of a compound. The molecule of a compound contains 2 or more different types of atoms chemically combined together. Atoms of different elements join together in definite proportions to form molecules of compounds. Let us consider some examples. In the compound water, the combining elements are hydrogen and oxygen. The ratio of hydrogen and oxygen is 1:8 by mass. The atomic mass of hydrogen is 1 and that of oxygen is 16. The mass ratio by atomic mass for hydrogen is 1 and that for oxygen is 1/2. Therefore, the simplest ratio of the combining atoms is 2:1. In the compound carbon dioxide, the combining elements are carbon and oxygen. The ratio by mass of the combining atoms is 3:8. The atomic mass of carbon is 12 and that of oxygen is 16. The mass ratio by atomic mass for carbon is 3/12 and for oxygen it is 8/16. Therefore, the simplest ratio of combining atoms is 1:2. In the ionic compound calcium oxide, the combining elements are calcium and oxygen. The atomic mass of calcium is 40 and that of oxygen is 16. Thus, the simplest ratio by mass of the combining ions is 5:2. In the compound magnesium sulfide, the combining ions are magnesium and sulfur. The atomic mass of magnesium is 24 and that of sulfur is 32. Thus, the ratio by mass of the combining ions is 3:4. In the compound sodium chloride, the combining ions are sodium and chlorine. The atomic mass of sodium is 23 and that of chlorine is 35.5. Thus, the ratio by mass of the combining ions is 23:35.5.
Let's do a quick check.